Welcome to Applied Flow Technologies AFT Impulse Quick Start video tutorial. This tutorial will teach you the fundamentals of using and understanding AFT Impulse. Prerequisites include an undergraduate engineering course in the analysis of pipe system fluid mechanics, as well as familiarity with standard industry practice in pipe flow analysis. AFT Impulse is a general-purpose tool for modeling pipe network waterhammer and pressure surge. Impulse simulates steady-state and transient behavior in liquid pipe networks. AFT Impulse also implements the method of characteristics for transient surge analysis, and optionally the discrete vapor cavity and discrete gas cavity models for cavitation. AFT Impulse models all liquid systems in which the fluid density, dynamic viscosity, and bulk modulus do not change within a single pipe. AFT Impulse also models Newtonian and non-Newtonian fluids using a number of different models. Impulse models systems that are pump, gravity, or pressure driven. Some components that can be modeled include known pressure or flow boundaries where the conditions can change with time. Also, there are multiple pump models available where you can model pump speed that can change with time. You can also account for pump inertial effects. Centrifugal pumps and positive displacement pumps can be modeled. Also, pumps with flow and pressure controllers can be modeled. Standard valves, control valves, relief valves, and check valves can all be modeled where their valve position can change with time. Surge suppression equipment such as gas accumulators, liquid accumulators, surge tanks, and vacuum breaker valves can also be modeled. The engineering assumptions and limitations of AFT Impulse is that wave speed stays constant during the transient, non-condensable gas release is negligible, and pipes are liquid full and fluid is single phase. Waterhammer is a transient phenomenon that occurs in liquid piping systems as the hydraulic behavior adjusts to changing conditions. Waterhammer can be caused by many events including valves closing or opening in full or in part over time, pump speed changes, relief valves cracking open and closed, tanks that are pressurizing over time, or periodic changes to pressure and flow conditions. Waterhammer can occur in any liquid piping system. The term waterhammer confuses some because it implies a process only in water systems. This is not true, as transient pressure waves occur in all systems that experience a change in operating conditions regardless of the fluid. Using AFT Impulse, you can accurately model transient events throughout your system and review the resultant transient hydraulics. In this tutorial, we will be changing all of the default units from English to metric. This can be done in the User Options, which is access to the Tools menu. You will be prompted to use these preferred units in the output as well. You can choose any or all of the preferred units to be applied to the output parameters. AFT Impulse is broken up into 5 primary windows. The Workspace and the Model Data windows are primarily for building and defining your model, while the Output, the Graph Results, and the Visual Report are primarily for reviewing the results. Let's explore the Workspace in more detail. To build a model, you will be using the toolbox on the left-hand side of the Workspace window. To draw a pipe on the Workspace, simply click on the Pipe Drawing tool and then draw a line where you would like your pipe to be located. Easily move the pipe's endpoints by clicking the pipe to select it, then clicking and dragging the endpoints wherever you like. To place a junction onto the Workspace, simply click on the junction and then drag and drop it onto the Workspace. To move a pipe or junction, simply drag and drop it where you would like to move it to. To move one end of a pipe, you can either move the connected junction, or you can drag and drop the handle onto the end of the pipe. To enter input data, simply double-click on the pipe or junction and a Properties window will open. The Properties window is the platform for entering data to define the pipes and junctions throughout your model. To help you identify the minimum required input data, we have highlighted those cells in blue. We will be disabling the blue highlight feature for this quick start tutorial in order to make data entry easier to see. To toggle the highlight feature on or off, you can double click in the background of any properties window, or you can press the F2 key on your keyboard. There is a model status light in the lower right corner which will turn green after you are ready to run your model. If you click on the model status light, a checklist will be displayed outlining what must be completed prior to running your model. The checklist can also be accessed through the View menu. The steady solution control is defined by default. The default steady state solution control parameters will solve the steady state for the majority of cases. The System Properties window is where you define your fluid data, your viscosity data, and your system data. In order to fulfill the Define Pipes and Junctions checklist item, you must construct your model in the Workspace and fill in all the required data for each pipe and junction. The Section Pipes checklist item can only be completed after all the pipes are defined throughout your model. The Transient Control checklist item can only be completed after completing the Section Pipes checklist item. Now let's dig a little deeper into the toolbox. The Pipe Drawing tool allows you to draw pipes on the workspace. Keep in mind that every pipe must be connected to a junction at either end. The minimum required input data for a pipe includes the hydraulic diameter, the pipe length, the friction model, and the wave speed. To help you define your pipes, we have provided a pipe material database which allows you to select standard pipe materials, sizes, and schedules. The reservoir junction acts as a pressure type system boundary, sourcing or sinking fluid to or from your system. The area change junction acts as a source of reflection for propagating transient pressure waves. This junction balances mass flow so that all flow into this junction is equal to all flow out of this junction. The valve junction can be defined with either a constant loss factor or with a user-defined transient where the valve opens or closes over time. Now let's build a simple fluid delivery system where one pressurized tank is delivering fluid through a run of pipe into another tank. We will model the effects of closing an actuated valve over different periods of time in order to see how slow we must close the valve in order to avoid cavitation. Although it was not shown here, the model was just saved as quickstarttutorial.imp. The system fluid will be liquid ammonia at 24 degrees Celsius. Notice the significantly high vapor pressure of liquid ammonia. If the system's static pressure drops below this value, the system will cavitate. Notice that the system properties are now defined. Now we will build the model using the toolbox on the left. Notice that as you hover over an icon in the toolbox, there are shortcuts that appear in the bottom of the left pane. If you double-click the pipe drawing tool, you'll be able to draw multiple pipes consecutively without having to re-click the pipe drawing tool every time. Now let's enter input data for the pipes as shown below. All pipes will be standard schedule steel ANSI pipe. Now let's enter input data for the junctions. The elevations are shown below. The pressurized supply and delivery tanks are controlled at a pressure of 17 bar G, and the area change will be modeled as an abrupt transition. The CV entered here represents the initial steady state CV for this valve. We are modeling a half-second valve closure, and we are going to assume that the valve closes linearly. Here we can see that the CV of the valve decreases from its initial steady state value of 1000 to a closed position over half a second. Notice that this transient is set to begin at t equals 0 seconds, beginning from the initial steady state conditions as determined by AFT Impulse. Notice that the Define All Pipes and Junctions checklist item is now complete. At this point, we are able to work on the section pipes and transient control checklist items. AFT Impulse uses the method of characteristics to predict how transient pressure waves propagate throughout the system. In order to apply the method of characteristics to a system, you must set up a characteristics grid in which all pipes can be broken into an integer number of section lengths. The number of sections that each pipe is broken into can be calculated using the following equation, where A is the wave speed of the fluid in a pipe, L is the length of the pipe, delta T is the time step, which is equal to the length of time for a pressure wave to move through a given pipe section. Keep in mind that each pipe section has a computation station at either end, therefore the more pipe sections you have in the pipes throughout your model, the longer the runtime. The process of setting up a characteristic grid is difficult and complex to perform manually. AFT Impulse's Section Pipes window automates the process of finding the optimal sectioning combinations. For more information on the details of the characteristic grid as used in the method of characteristics, please review the AFT Impulse pipe sectioning video tutorial on our website. Now that we have completed the task of sectioning the pipes throughout the model, we can set up our transient control. The transient control window allows you to fine-tune how the transient simulation will be calculated and saved into output. We will leave all of the defaults set, including the option to model transient cavitation, and change the simulation duration to 5 seconds. Notice that all of our checklist items have been completed and we are now ready to run the model and review the results. Each new model must first be saved before you can run it. This model has already been saved as quickstarttutorial.imp, so now we'll run the model and review the results. The output window is broken into 3 sections: the general section at the top, the pipe section in the middle, and the junction section at the bottom. The results shown here are the transient max-min results. The easiest way to review the transient results is through the graph results window. The purpose of this model is to determine a valve closure time such that we avoid cavitation. The easiest way to identify cavitation for this system will be to plot the vapor volume against the total pipe length. Note that this graph will show the maximum values that occurred at any time throughout the simulation duration. We can see that there are vapor volumes, and therefore cavitation, present when we close the valve over half a second. The goal of this example is to determine a valve closure time that eliminates the cavitation. Before changing the valve closure time, let's briefly discuss some helpful graphing capabilities that will greatly aid you with your waterhammer analysis with AFT Impulse. Multiple graph tabs can easily be created, which allows you to view multiple graphs very quickly in separate tabs. The Graph List Manager is a very convenient filing system that allows you to store multiple graphs in graph folders. This helps keep your graph list items well organized so you can quickly access commonly used graphs. Before we change the valve transient, let's add this graph to the Graph List Manager so we can quickly access this graph again later. Simply click the Add Graph to List icon on the Graph Results toolbar and then give the graph a name. This graph has now been added to the default My Graphs folder in the Graph List Manager. You can create as many separate graph list folders to the Graph List Manager as you like. You can also add as many graph list items to each individual graph list folder as you like. Multiple graph types, like the transient pipe graph, transient junctions, and profile plots, can be added to the same graph list folder. Easily load and view graph list items in many ways. Double-click a graph list item to load it into separate graph tabs. Right-click a graph folder to load graph list items into separate graph tabs. Or right-click the graph folder to load graph list items into a single graph tab. The dark green border means that the selected graph and graph parameters belong to the associated graph list item. Let's try changing the valve closure time to a 1-second closure. Although lengthening valve closure time did not eliminate cavitation, it did reduce the vapor volumes. Let's try a 2-second valve closure. As is shown by the absence of vapor volumes, a 2-second valve closure does not result in cavitation. Now let's animate the transient pressure profile of the 2-second valve closure. Another useful graph is the max-min transient pressure profile. As you can see, the maximum pressure in the system is about 25.6 bar, while the minimum pressure is about 12 bar, which is above the 10.1 bar vapor pressure, and thus the cavitation has been completely eliminated by closing the valve over a 2-second time frame. This concludes the AFT Impulse Quick Start tutorial. Thank you for watching, and please visit our website at www.aft.com/learningcenter/videotutorials to watch our extensive library of other AFT video tutorials.